Welcome to Metallurgy Review, Part 2. Critical cooling rates. The slowest continuous cooling rate produces 100% martensite. If we go back to our isothermal transformation diagram, our critical cooling rate is the slowest rate, which is degrees per second. So we're going to start up here at an elevated temperature, right? And we're going to cool at some rate. We're going to miss the nose of that curve, and we're going to end up down here in martensite. That's our critical cooling rate for this diagram right here. Because if I cool it any slower, I'm going to end up over here, and I'm going to get into that zone. Once I start forming bainite or perlitic products, I can't go back because I can't go in this direction at all because I can't go back in time. So when I hit that nose, my transformation has started, and I have to keep moving forward. So the slowest cooling rate is one that just misses this nose. But more importantly, why does it matter? Why not take our steel and pull it out of the oven and quench it in liquid quench it in liquid nitrogen? What would be the problem with that? Well, if I cool it too fast, I induce too much stress. And if my stress exceeds the strength of my material, I end up with cracking. So the slower I cool it, the more time I give it for that stress to relieve. The more time I give it for the stress to relieve, that means my overall stress level is lower, and I don't end up with what we call quench cracking, or what is the term? Thermal shock. Impact due to change in temperature. What happens to the size of my block of steel when I heat it up? It expands, right? I'm exaggerating, but it expands. And this is a change in dimension, correct? And a change in dimension is strain. If I have strain, I have to have stress. So even though I am going from my big size down to my small size because I'm cooling down, I am still changing dimension, which has stress associated with it. So that stress, change in shape, change in size, so that thermal stress there, plus what we call dilation stresses, you don't need to know that term, but that is when we go from FCC, which is our crystal structure when we're up here at high temperatures, right? We're austenite, which is FCC. When we change to body-centered tetragonal, which is what we are down here in martensite. So when I go from this up here, which is FCC, and I cool it down to my BCT down here, this right here is a change in crystal structure shape, which is strain, which has a stress associated with it. And this stress, my thermal stress, plus my dilation stress, is my total stress. And if my total stress exceeds the strength of my material, I have failure. So the more time that I have here, more time for my stress to reduce, the less failures that I have. That's why our critical cooling rate is so important. Retained austenite, which is on page 215, is austenite that has survived the heat treatment cycle, and it did not kick over. Now, we've said that on our iron carbon phase diagram, we have our 1333, we have our upper critical temperatures, we have our austenite zone, which is up here, we have 0.8 here. So this is 1333. So if we're in our austenite zone and we slow cool it, we're not going to have any retained austenite. It's only when we quench it do we have it. And we keep saying that austenite is not stable below 1333, right? It wants to break down and turn into something else. And if we look at our isothermal transformation diagrams, we have our 1333 line up here. We're starting here, and we are cooling it at our critical cooling rate. We're ending up down here at martensite. Well, this is my start and this is my finish. How can I have any austenite that's left over? Well, austenite, which is FCC, has got to go over to down here, BCT, to turn into martensite, right? So I have to literally rearrange all of my atoms, and that takes energy. Most of the steels that we're quenching are alloy steels or tool steels. The more alloys we have, the more time we have to go from here to here. Why is that? Because alloys retard the movement of our atoms. Alloys make it harder to go from FCC to something else. So that's how it gives us way more time. Well, if the alloys are doing too good of a job, the FCC never kicks over and turns into body-centered tetragonal. So we end up with retained austenite. Why doesn't it kick over once it gets down at lower temperatures? Because it doesn't have enough energy. It takes a certain amount of energy to get my atoms to totally rearrange. Remember, diffusion rates. The diffusion rate of iron in steel is relatively slow at room temperature. It's almost non-existent. So it takes energy to cause that to kick over. So understand what retained austenite is. How do we get rid of it? Usually multiple temperings. So we'll double draw, triple draw, as the trade term might be. Drawing and tempering are the same thing. Specific heat treatments of steels, Chapter 14, which starts on 217 in your textbook. Heat treatment. This would be a good definition to know. The process of heating and cooling metals in order to obtain desired properties. This is what we've been talking about 80% of the semester. Austenizing, pretty simple. We're heating it up into austenite. Hold time. This is more of a formality understanding, but know the definition here of hold time. The holding at an austenizing temperature long enough to soak the entire part so it kicks over and everything is equalized. The temperature and microstructure. That's why we hold it at our austenizing temperature for a certain amount of time. The rule of thumb is an hour per inch of thickness. So hold time or soak, hold or soak time is the same thing, and it's usually an hour per inch of thickness. Although this is a rule of thumb, it is not an absolute. You still need to look that up, because in some alloy steels or tool steels, you are going to preheat, you're going to high heat, which is your austenizing temperature, and then you're going to quench. So you might hold at your preheat time, and then your high heat is at a very specific time, like 10 minutes or 15 minutes or whatever it is. It's not dependent on material thickness. So you still need to look up your heat treating procedure in either your machinist handbook, the heat treater's Bible, the manufacturer's website. Some of these locations, you need to look that up. Quenching. If I rapidly cool, if I fast cool, or if I quench, they are all the same thing, and they are going to turn out as martensite. And that's really what determines what quenching is. Because if I take a piece of 1008 steel and I austenize that, let's say I heat that up to 1700 degrees, and I pull that out of the oven and I dip it in cold oil, did I quench that material? No, because my product is going to be perlitic. It's going to be perlite and ferrite. It's going to be perlitic. So I did not quench it. Even though I dipped it in cold oil, that's not going to get it. And if I dip that in let's say I dipped it in 200 degree water. I suspect this 1008, which has very low hardenability, that I'm going to end up with perlite and ferrite again, or at least in some of those areas. So I need to cool this very, very, very fast for it to be quenching. I may need to cool 1008 in room temperature or even cold water to get that to turn over to martensite. Nothing on quench mechanisms. Oh, quench mediums. Why do we use the different quench mediums? It's all about critical cooling rate, right? We just talked about thermal shock. I could take my A2, which is an air quench material, I could dip that in water, and I'm going to get martensite. There's no doubt about it, I'm going to get martensite. But I'm going to cause too much stress, and I could induce cracking, which I don't want. So we want to cool it as slow as possible to reduce stress, reduce cracking, and I am going to choose one of these for any given material that's going to give me the cheapest cost, right? So I can dip A2 in hot oil, probably not going to cause a lot of problems, but why would you go through the hassle? Because now I got to have oil tanks, I got to have heaters, why would you just pull it out of the oven and set it on the bench? It's free. So we want the lowest cost that's going to give me the products that I want. Tempering. So when do we temper? Time-wise, you try to do it as soon as possible after quenching. When is it necessary to temper? If you form martensite, you should be tempering it. That's just the bottom line. So tempering is super important because we know that martensite, left alone, left untempered, is going to be high stress, and high stress leads to cracking. It's what we call a subcritical process because it's below our 1333, below our critical temperatures, and the goal is to increase ductility and toughness. Now, reducing hardness, this may or may not be a goal. It is a byproduct, but we may not necessarily want to reduce hardness, but you're going to reduce a little bit. In other situations, we might temper at high temperatures to drop our hardness, which is going to increase our toughness and ductility even more yet. So, tempering is a necessary part of austenizing, quenching to form martensite, and then tempering. So we would call this quench and temper, Q&T. So that's a very common term in industry. You're going to Q&T or quench and temper, because that's what we're going to do to our steels. We're going to austenize and quench them to form martensite, and then you must temper them. Interrupted quenching techniques. So we talked about austempering and martempering, and if I look at my isothermal transformation diagram, which is not a very good one here, but it's going to work. So if for austempering, I am starting up here, and I am going to quench it in hot oil or molten salt bath, and I'm going to end up over here in my bayonetic products. For martempering, I'm going to quench it down just above my martensite start, and then quench it to form martensite, and then I'm going to reheat it for tempering, and then back down to room temperature. So I have austempering and martempering. They're my interrupted quenching techniques, and they will produce low stress martensite for my martempering or bainite for my austempering, and that's really what we need to know about them. Austempering produces bainite. Martensite is low stress martensite. Annealing. Annealing is a whole group of processes. So annealing, as far as steels go, produces perlitic microstructures. That's what annealing as the term means. Full annealing is what people think of when you say annealing, but that's taking a hardened steel, austenizing it, cooling it in the oven to produce a soft, coarse perlitic microstructure. And coarse means large grain size. Normalizing is an annealing process because we're producing pearlitic microstructures. But normalizing is heating our steel up just above the upper critical temperature, which is going to be austenite, cooling it in air. It's going to decrease my perlite interlamellar spacing, and it's going to refine my grain size. This is the important part right here, refining grain size, meaning making it smaller, which is going to increase ductility and toughness. So normalizing is a very common process with our alloy steels and tool steels. And a lot of the materials that you buy are already normalized. So what's interesting here is full annealing and normalizing are for transformation strengthened materials. Process annealing is for cold work materials. And this is removing all of your cold work. That would be 100% process annealed, or partial process annealing is just to restore ductility to our cold work steels. Because when we cold work them, our ductility goes way down. So we need to get that ductility back. So we process anneal it a little bit. If we heat it up too much, we'll wipe out all of the cold work, and then it'll be right back to what it was when it was before cold working. Stress relieving on page 227, that would be a good definition to know. Case hardening, just the gist of case hardening, leaving the core alone, only hardening the outside surface layer. If I ask any questions about that, it will only be about the two different types, which would be altering and maintaining, the two different techniques. The subcategorize like carburizing, I won't ask about that. Just about maintaining and altering, maybe what is the difference between the two. I might have you list the two different types, something like that. Tool steels. Tool steels are basically steels. They're just a different category, and they have typically more alloys and more carbon in them, although not always true, but that's kind of what classifies them as tool steels. But they are, like any other steel, that act the same way. So there are 7 different categories of tool steels, and I might ask questions about what are the 7 categories. On page 239 in your book is the tool steel identification chart. I would tab that page for sure, and I might ask some questions like, 01, what is the carbon content, what is the alloy content, something like that. So you'll want to tab that page so you can look them up. Page 251 in your book is where cast irons start. If we look at the iron carbon phase diagram, we find that our cast irons are between 2 and 6.67% carbon content, and that's really kind of the layman's method of defining what cast irons are. Is they are an iron carbon alloy with 2 to 6.67% carbon content. What is the difference between cast irons and steels? Steels have less than 2%, and cast irons have 2 to 6.67% carbon. That's kind of the layman's terms, easy way to explain it. Not all cast irons are in the cast form. Some of them are in the wrought form or worked castings. I won't ask about the alloys. The different categories or different types of cast irons, should be able to list them. On page 253 and page 255, there are some gray iron designations, malleable iron and ductile cast iron designations with material properties. I would expect a designation type question, like I might give you a ductile cast iron grade, and you'll have to look it up on one of those 3 charts that are on these 2 pages here, and look up maybe tensile strength, yield strength, maybe percent elongation, something like that. What is the difference between the different types of cast irons here? Remember, we talked about the carbon groupings. Here we have graphite flakes. Here we have distribution of carbides. Here we have the little fuzzy cotton ball looking things. Ductile iron, we have spheres. Compacted graphite, we have the weird shapes of the carbon groupings. So where is the carbon and what does it look like? That's the difference between our cast irons. Most of our cast irons can be perlitic, they can be ferrite, I shouldn't say perlitic, they can be perlite, they can be ferrite, or we can austenize and quench and temper them and turn them into martensite. So most of our cast irons are that way. Stainless steels. What makes stainless steel stainless? Which is chrome. What's the minimum amount of chrome necessary? 12%. Technically it's 11.5, but the book says 12, so we'll go with that. What does our chromium do? It creates this passive surface oxide, which provides corrosion resistance. What are the two main reasons that we use stainless steels? Corrosion resistance and high temperature strength. You should be able to list the 6 different classes or families of stainless steels. On page 264 is a selected designations for stainless steels. There's kind of a little list there. Extra chrome and extra aluminum help strengthen the passive film, which means it gives us more corrosion resistance, more high temperature strength. Carbide formers tie up carbon, prevent chromium carbides, which we call these stabilized grades. I won't ask any questions about the Scheffler diagram, although if you get into working with stainless steels from the design standpoint and selecting alloys and welding these, you're going to be using some sort of constitutional diagram, which I had mentioned before. The Scheffler diagram is the one the book talks about, but there are several of them. It's got some different types of stainless steels, starting with martensitics. The designation chart for martensitics is on page 268. On 269 for our ferritic stainless steels. 272 for our austenitic stainless steels. 276 for our precipitation hardened stainless steels, which are broken down into 3 categories of martensitic, semi-austenitic, and austenitics. So on those pages there, I would tab at least the beginning of them. You can find most of the rest of them there, but I will probably give you a stainless steel, like, I don't know, maybe a 440 or a 410 or 312 or something that you're going to find on one of those charts. I'm going to ask some questions about that. I'm going to ask maybe what is it, strengthening mechanism, how do we anneal it, can we heat treat it, what alloy group is it. Like 440 is a martensitic. I happen to know that one off the top of my head. But if you go back to page 268 and I said 440C, what group is that under? Well, we're going to find that on page 268 in the upper right hand corner. So we know that that one is a martensitic. And what is its strengthening mechanism? It's a transformation strengthening, meaning we can austenize, quench, and temper. And how do we anneal it? We're going to heat it up and slow cool it in the oven, and we'll talk about that. In this chapter, under each of the headings of the material types, it has strengthening mechanisms and how to make it hard, how to make it soft. So that's all right there underneath those paragraph headings. Aluminum, which starts on page 233. Different shapes, strength, it's about 1/5 the tensile strength of our structural steels. Our non-heat treatables, that starts on page 334. We break our aluminum down into two groups, right? Our non-heat treatables and our heat treatable alloys. Our non-heat treatables are solid solution or cold worked only. We cannot heat treat them to make them harder. Our heat treatables are precipitation hardened, and these are heated in an oven at low temperatures for long periods of time to age harden them. And age hardening can either be done naturally or artificially. We talked about that a little bit. If I can cold work them to make them stronger, I can anneal them. And if I can precipitation harden them to make them stronger, I can anneal them. On page 335 is our AA designation, Aluminum Association designation chart. I would tab that page. I would expect a question about alloy group and strengthening mechanisms, and maybe even how to soften them. And on page 334 is where it starts talking about strengthening mechanisms, and talks about solid solution, cold working, precipitation hardening. And then on the top of page 335 it talks about annealing or softening them. So that's all right there in that small area. If I give you an alloy, say like 2024, you'd look it up on that chart on the bottom of page 335. And at the Aluminum Association, we know that we're looking at the first digit here, right? So this is really a 2000 series. That's really all we care about. So on that spider diagram on the bottom of page 335, at 12 o'clock, we can see that that box, which is, it says aluminum copper, in an upper right hand corner it says pH. Oops. It says pH for precipitation hardening, and then just outside of that it says 2XXX. That's my 2000 series. So this is that box at 12 o'clock. So what group or family is it? It's aluminum copper. What is its strengthening mechanism? It's a precipitation hardening. And then on page 334 and 335, if I ask questions about how do I harden it, how do I soften it, it's right there in that reading. Strengthening mechanisms. One note here is this chapter is not in your book. Remember, we did chapter 4 PowerPoint. We read chapter 4 in the book, but there are no questions out of chapter 4 out of your book. Just chapter 4 PowerPoint. And you should be able to list the 5 strengthening mechanisms and a short 1-sentence explanation of what they are. And like solid solution strengthening, adding alloys in solution to strengthen the microstructure, crystal structure. Transformation strengthening, transforming from a soft structure to a hard structure. Precipitation strengthening, precipitating alloys out of solution to form intermetallic compounds. Strain or work hardening, mechanically causing dislocations in the crystal structure. So just very simple 1-sentence explanation of what are the strengthening mechanisms. And dual phase was not on there. We have not talked about dual phase that much at all. So really the 1-sentence explanation are about the first 4, but you should be able to list all 5 of them. On Blackboard, I will post the final exam. There will be probably another tab down here, for exam, and you'll be able to click on that and be able to open the exam. So I will have another audio on instructions for the exam, when it will be available, how long it will be available, test requirements, limitations, all of that. I will have that posted for you as soon as I can in the next few days. But make sure that you have checked your homework grades on Blackboard. Make sure that everything is posted. If I have missed something that you've turned in, resend that to me, and I will post those grades. If you haven't got your homeworks to me yet, still have time to get them in. A lot of you have turned in your special report already. That's wonderful. Make sure you get that to me as soon as you possibly can. Technically it's due today, and then that leaves us through next week to study for the final exam. So hang in there, we're almost there.